Hello, my name is Dawn Andrews, and I am a graduate of the Georgia Institute of Technology from the Space Systems Design Lab in the Glenn Lightsey Research Group. I will be presenting on my master's research, which was the design of a green monopropellant propulsion system for the Lunar flashlight mission. This opportunity was made possible through collaboration with the NASA Marshall Space Flight Center and the Jet Propulsion Laboratory, and we are very grateful to them for their support throughout this project. The Lunar Flashlight mission is a 6U CubeSat mission that will be heading to the Moon along with the Space Launch System's first flight. It is one of several of NASA's exploratory missions in advance of reestablishing a human presence on the Moon. It hopes to contribute critical science by surveying the South Pole with lasers and spectrometers to characterize the presence of volatiles, including water ice. The 6U CubeSat includes a green monopropellant propulsion system whose design and realization is being worked by Georgia Tech and NASA Marshall. This system is responsible for providing the propulsive capability to maintain course for the Moon and eventually insert the CubeSat into its desired science orbit. To do so, the monopropellant system carries the AFM-315E monopropellant, which is a hydrazine alternative that gives it the green monopropellant moniker. It also includes 4 100 millinewton thrusters, as well as several custom-developed microfluidic components, like the system's pump and valves. When the project was granted to Georgia Tech, we inherited a set of pre-existing requirements, including a very tight trade space for mass, volume, and impulse. In addition to that, the propulsion system already had a fully defined interface control document between the spacecraft and the propulsion system. So this left the trade space highly constrained, and despite that, the project also took on some necessary and fundamental architectural changes that would help maximize the mission's probability of success. Notably, we chose to leverage additive manufacturing in the design of this system, which gave us the flexibility to close the design and provide a uniquely custom solution for this mission. Additive manufacturing, and specifically laser powder bed fusion, has challenges of its own that we considered through the design process. The thermal gradients and layer-by-layer buildup have to be considered during design in order to prevent cracking of the structure and any partially fused powder. And our design also had a post-print machining step to be considered as well. Before jumping into the design of the propulsion system itself, I wanted to give a brief overview of monopropellant propulsion and emphasize the benefits of green monopropellants. Monopropellant propulsion is the decomposition-based form of chemical propulsion in which a single fuel is flowed through a catalyst bed in a thruster that causes the release of chemical energy. The reacting propellant can then be accelerated out through the nozzle to provide thrust. Monopropellant propulsion is a good middle ground between your classic and usually very complex bipropellant propulsion and the simplicity of a cold or warm gas thruster, which relies solely on pressure gradients to give very small amounts of thrust. By nature of including chemical energy as part of the equation for its propulsion, it is higher performing than any cold gas thruster, and yet can be packaged at a much smaller scale without the machinery necessary for a full combustion engine. However, monopropellant propulsion has its challenges as well, and most notably the hazards involved with handling, testing, and firing hydrazine thrusters make these systems inaccessible to many small-sat missions. Instead, one of NASA's key technologies focuses on alternatives to hydrazine, which mainly include 2 hydroxyl ammonium nitrate candidates, LMP-103S and AFM-315E. Both propellants were considered during the design of the Lunar flashlight system, and ultimately we chose to use AFM-315E, which, compared to hydrazine, provides safer handling, improves stability through storage and environmental exposure, decreased toxicity in the case of contact or firing of the monoprop thrusters, and it even has a competitive performance density over hydrazine, as seen in the table below. So back to the Lunar flashlight mission's propulsion system solution. Our design is a pump pressurization architecture that is essentially addressed through a tank subassembly and a manifold subassembly. The system as a whole also includes a custom suite of avionics to monitor and command the system. It has its own thermal sensing and control systems, which is super important for our choice of propellant, and it includes consideration to liquid management on orbit. At the beginning of the project, the pump-fed architecture was traded against a blowdown pressurization approach and even a cold gas system just to have a baseline. But ultimately, this schematic was chosen in order to maximize the performance that we could get out of an otherwise fully constrained trade space. The PNID schematic in the bottom right shows all the components of the propulsion system, and it's worth mentioning that nearly every single component will be on its first spaceflight. The first half of the propulsion system is the tank, which is a welded titanium structure whose primary responsibility is to contain the AFM-315E throughout launch and on-orbit operations. Because of this, the tank holds to strict fracture control, fault tolerance, and hazard risk requirements. So, during its design, a few different manufacturing methods were traded, but ultimately this tank was designed for simplicity and well-proven processes in order to absorb any possible risk to the SLS and its primary mission. There are a couple of fun points to mention in the design of the tank. You can see in the picture at right that rectangle is a rather unconventional shape for a pressurized fluid tank, but that decision was actually driven by the packaging requirements on the system. Of the 2.5 U that were dedicated to the propulsion system, nearly 2/3 of that volume had to be allocated to the propellant itself. Here, we iterated between design and finite element analyses several times in order to be certain that we could close our pressure requirements with the necessarily large safety factors. And secondly, the tank includes a propellant management device since it is such a large volume filled with both liquid and ullage on orbit. Our PMD uses capillary action and surface tension to ensure that the tank outlet is always wetted when firing, since there is no natural sump to the tank nor any other external forces to direct the propellant before you begin firing. The other half of the system design is the manifold. Whereas the tank was designed for simplicity, risk reduction, and very careful compliance within strict requirements, the manifold addresses pretty much all of the rest of the complexity in the system. We chose to additively manufacture the manifold from grade 5 titanium, which allowed us to print all of the fluid lines and structural interfaces into a single continuous piece. The choice to additively manufacture this part gave us significantly more flexibility for volume packaging and mass savings, which were by far the tightest two constraints on the remaining design downstream of the tank. This manifold takes responsibility for tying together the thrusters, the valves, the pump, the avionics, sensors, as well as all of the fluid routing. You can see the raw print in the image at right, which sort of indicates all of the structural mounting that's involved on the exterior of the piece, but buried inside that piece as well is the fluid passages that you would traditionally associate with a propulsion system. All in all, an equivalent system using standardized lines and fittings would include upwards of 40 distinct components and custom machined interfaces, and packaging would have been extremely difficult. This project is continuing development after successfully passing its critical design review in January of 2020, which led to the next phases of our project where the manufacturing, integration, and test has begun. It's also important to mention that the electronics development has also been occurring in-house, also in Dr. Leitz's research group, but under a separate contact that is funding our avionics team in their progress. Their work has been occurring in parallel alongside the structures and prop-focused systems development that was discussed here, and it has been awesome to work hand in hand with that team and see the system come together all at once. Upon completion, the Lunar flashlight mission would become the first CubeSat to perform an orbit insertion and enter orbit around a planetary body other than Earth. Its propulsion system would be the first demonstration in space of green monopropellant used in a CubeSat form factor, and finally the propulsion system will help Lunar flashlight become the first CubeSat to go to the moon. This project has been an amazing opportunity and has had an outstanding team, and I know we are all looking forward to contributing the propulsion system to such an exciting and ambitious mission. Again, thank you to NASA Marshall and JPL for providing this opportunity in collaboration with the Georgia Tech Glenn Leitz's research group, and thank you as well to the rest of the student team that made working on this project a real honor and a pleasure. I wish you all the best in the continued development for this project and this mission, and I look forward to seeing this propulsion system circling the moon.